we will really enjoy this lecture. And I will say the floor is yours.
Okay, thanks very much. I will share my screen. So is everybody seeing the first page of my presentation?
Yes, looks great.
Okay. So yeah, thanks very much for the introduction and for the opportunity to talk at the researchers desk. So yeah, my name is Iain Pitcairn. I'm Scottish. I lived in Sweden for almost 20 years, and I'm a researcher at the Department of Geological Sciences at Stockholm University. So I carry out mainly research on ore forming processes, the processes that form ore deposits. And what I'm going to talk about today is the role of mineral deposits in the green energy transition. Okay. So just a couple of slides on the background, just so that you all know really what I'm talking about. What is a mineral deposit? Well, it can be defined as being where a useful commodity is sufficiently concentrated in an accessible part of the Earth's crust to be profitably extracted. So it requires concentration processes. So these are geological processes that cause an increase in the concentration of a metal or a mineral to such an extent that when it's exposed at the Earth's surface, it can be mined. The term profitably is there. The word ore we often refer to, or malm, that's actually an economic term. That's something that we can mine at a profitable level. What's interesting about mineral deposits is that they are geochemical anomalies, and most of my research is on the processes that cause their enrichment. Sweden has a very long history of mining. I'm sure you're all aware of that, dating back many thousands of years. There is charcoal from a sort of a waste or a lake in the Garpenberg area in Bergslagen that's been dated at over 1500 years old. So we know that mining has been ongoing for at least 1,500 years. Sweden is currently one of the EU's leading producers of mineral resources. 90% of Europe's iron ore, 20% of base metals. Base metals are referred to as copper, zinc, and lead. It's a large gold producer, and many of the employs much of, or a proportion of Sweden's industrial workforce is employed in the minerals industry. These are the mineral deposits which are currently being mined in Sweden. There's not that many. There are 12 active mines being run and 3 main regions where we mine ore. So Norrbotten, which is dominated by iron ore, with obviously the famous Kirunavaara deposit in Kiruna. Then we have the Skellefteå belt, which is dominated by base metal mineralization, driven mainly by Boliden. And then we have also the Bergslagen area, which is also contains mainly base metal mineral deposits. But it wasn't always like that. 100 odd years ago, Sweden had hundreds of mines, up as many as 500 mines around the time of the First World War. But the production of ore was very small compared to today. So what you can see that's happened is, of course, the number of mines has drastically decreased from around 400 to 500 down to 12. But those mines have grown in size greatly. And the production of ore that we see today is much, much bigger than it was back then. And now we produce, the majority of ore we produce is iron ore for concentrating, and also the non-iron ore that shows on this diagram is dominantly the base metal and gold resources. So Sweden, you would say, it has a strong mining history, but it also produces a lot of the mining focuses on what I would call the traditional metal resources: iron, copper, zinc, lead, base metals, and gold. But times are changing. New technologies, electronics and things like that require a much greater range of metal or mineral resources than previously. And some of the technologies that you see in this kind of cartoon diagram here include solar cells and wind turbines, and they require a lot of mineral resources in order to be produced. So we're at a situation now where our technological advancement requires a much greater array of different mineral resources. And in particular, the transition towards renewable energies requires a much larger mineral resource than we previously have needed. This is what I'll go on to show in the rest of the talk. The classic example that everybody uses in these talks is the example of a smartphone. So we all have smartphones, I'm sure, and they contain, or they're made from, around 60 to 65 different chemical elements. Many of them are used, for example, within the screen. We have indium tin oxide, which is what allows the screen to be conductive. We have a lot of rare earth elements, which produce the kind of brilliance and brightness in the screen. There's obviously the battery. Everybody will be aware of batteries contain elements such as lithium and cobalt and so on. And there's also the electronics. Of course, there's copper and gold and more traditional elements used in these things, but there's a whole load of other uses for the less traditional metals, things like rare earth elements and so on. So these devices are much more advanced. They require many more different types of chemical elements, and the chemical elements are often dissolved or used multiply, or multiple chemical elements are used in different components. And we'll see that this creates a problem when it comes to, for example, recycling. It's very difficult to get these mixed, blended components to allow them to be, the chemical elements to be easily recycled from these components. So this is where we are in terms of mineral resources and the transition to renewable energy. This is from a really interesting analysis by Simon Michaud, who works for the Geological Survey of Finland. And we're basically somewhere in this transition phase where we're moving from oil-based energy technologies. So for the transport system, we have oil-based internal combustion engines. For electricity generation, we're kind of moving from fossil fuel power, and in industrial processes, we're also trying to transition away from fossil fuel power towards renewable energies. And all of these require, what I'm going to show is all of these are going to have a large requirement for mineral resources, and in particular, a particular sort of mineral resource that I will refer to as critical metals or critical minerals. This is an example. The sources are listed at the side. I also have all the sources for these slides on the last page of the presentation, so they'll be available for anyone who wants them. Now, this is an example of renewable energy, or the mineral resources required for renewable energies within power generation and road transport. So this is calculated in terms of copper equivalent. Now, the reason for doing this is because most of these diagrams, they would be swamped by iron or steel because the requirement for those is so much that you don't then see these other small volume elements. So it's been written and calculated in terms of copper equivalent, which is the CuEq at the top of each slide. But the point here is that you can clearly see that as we move from coal and gas fired to more renewable energy such as wind and solar photovoltaic, we have a much higher material intensity. That means we need more mineral resources. And that's the problem we have. How do we get hold of these mineral resources? But of course, the benefit of doing it is the emission intensity goes down. So as the mineral resource intensity increases, the CO2 emission intensity decreases. And it's both the same for power generation and for transport. Now you see a number of elements listed on the left here, some kind of unusual elements, rare earths, cadmium, gallium, tellurium, things like that. I'm going to go on to talk about what these are and how we classify them. But first, this is just another diagram showing the same kind of scenario. Here it's put in terms of the different climate change related scenarios that we're hoping to achieve. So below 2 degrees warming or below 1.57 degrees warming and so on. What we see is that the better the transition, or the quicker the transition to renewable energy, the faster or the more likely chance that we're going to decrease our or we're going to allow ourselves to limit the global warming to a lesser degree. So if you look at the RTS, which is the kind of reference technology scenario, that's what we're currently, that's basically continuing as present. And we compare that to the 2 degree scenario or the below 2 degree scenario, you see that the demand for mineral resources increases hugely. So if we're going to transition to renewable energies, we need more mineral resources. That is undeniable. These are the types of mineral resources that we need. So we have geothermal, hydro, nuclear, and so on. And then we have the more, what we see as the traditional renewable energies on the right-hand side, wind power, solar photovoltaic, and of course, electric vehicles. And you see that as we move towards these, we have a much larger range of chemical elements that we require. We have a lot of rare earth elements, dysprosium, neodymium, praseodymium, and various other elements are particularly important for certain renewable energies. Tellurium, you'll see at the bottom, is obviously really only important for solar photovoltaic cells and so on. So if we're going to transition over to electric vehicles and wind power and solar photovoltaic, we need to make sure that we have these mineral resources that we see here. So these mineral resources we refer to as critical raw materials. What a critical metal or a critical raw material is an element that is important for modern technologies, including renewable energy, but that the supply is either limited due to limited resources, or it's under threat. And by under threat, that would mean that it is controlled by one country, essentially, so that we end up being in a geopolitical situation where the resource that's needed on a global scale is controlled only by one company. So all of the elements that are in the top right-hand side of this diagram, they can be described as being critical metals or critical elements. Things like rare earth elements are obviously highlighted at the top. They are very important for many of these renewable energies, electric vehicles, wind power, where we need strong permanent magnets in the wind turbines and various things. But there's lots of other elements in there. Cobalt you'll know about in terms of batteries and various other things. So many of these renewable energy resources require critical raw materials. And the question is, how do we get hold of those? Why are they critical? This is another set of definitions. This is just to point out that there are a number of different definitions of what is critical. The EU have had, they started their list of critical minerals back more than 10 years ago, and they've updated it gradually over time. SGU, the Geological Survey of Sweden, they also have a list of different critical minerals within Sweden. They started to call them innovation critical minerals in 2017. But we see the same kind of elements listed: rare earth elements, lithium, cobalt, nickel, all these elements that we require for batteries, and then other things that we require for electronics, things like germanium and so on. So this is, I now show a series of slides that show the increase in these critical mineral resources that we're going to require if we're going to transition over to renewable energies. So what this diagram shows is the present use of the elemental resource compared to projections from to 2030. And so you'll see that for many of the elements, for each, for wind, solar, and various different things, we see large percentage increases in the requirement of the chemical elements if we're actually going to transition towards these renewable energies in the way that we that is planned based on becoming moving away from fossil fuels based on the EU directives and so on. So for wind power, the key increases will be the rare earth elements, things like neodymium and dysprosium, which again are used strongly in magnets within the wind turbines. In solar, photovoltaic, there's a number of different elements, but we need an increase in tellurium, indium, tin, and so on. And, you know, I don't want to get into the details of biofuel and things like that, but the general message is that as we transition to renewable energy, we're going to need much larger volumes of these critical mineral resources. This is another slide showing a kind of similar thing, where they've chosen a series of elements that are particularly important. And as we're going to move towards, if we're going to keep on this 1.5 degree pathway, if it's even possible to keep on that at this current stage, we're going to move towards, what this shows is the percentage increase in the mineral resource that we need in order to stay on that pathway via transitioning towards renewable energies. So cobalt, we need 100% more production of cobalt, lithium, tellurium. So, you know, I'm duplicating what I've already kind of said, but what I'm showing is that for all of these mineral resources, we're going to need increased access to resources in order to build more of the renewable energy power stations and power producing mechanisms in order to transition away from fossil fuels. This is just a very simplistic graphic showing where we need the or showing what in total what we need for things like wind turbines. So it's, of course, I've talked about rare earth elements in the magnets and so on, but we're also going to need quite a lot of the traditional resources, things like copper and steel, and of course concrete are going to be required to produce these things. So that it's not just the critical minerals that we need in order to actually build these large wind parks. there's a burden of the kind of classic mineral resources as well, to allow us to produce this renewable energy. We talk a lot about electric vehicles. Everybody knows that, well, various European countries have said that they want to transition to electric vehicles by 2030 or 2040 or so on. And there are a large number of battery or factories, mega factories producing batteries. They're either in process or they're basically in production, or they're being built, or they're planned. So this is, all of these factories, including Northvolt and the different ones within Sweden or Fennoscandia, they're all going to need access to the mineral resources that we need to build the batteries in the first place. So at the moment, it's particularly lithium, cobalt, and nickel. As battery technology evolves, I'm sure certain elements, the demand or the requirement for certain elements may well change as the technology evolves over time. But just these planned mega factories for car batteries show the increased demand that we're going to need for producing these materials. Cars, we often talk about lithium and cobalt that we need for the batteries, but there's also a hugely increased use of rare earth elements in modern electric vehicles compared to older vehicles. There are, again, we have this mixture of materials, these in order to increase the kind of the quality, the technological advancement of modern cars requires the use of lots of elements. So here we have, for example, LCD screens, even polishing of glass and mirrors, various different things all require catalytic converters and so on. All of these things require rare earth elements. So our technological advancement, it has a burden on the mineral resources industry. We need to produce these elements somehow. So who are the major producers of critical metals? Well, there are quite a number of producers of spread around the globe: US, Brazil, France, Congo. You can see Democratic Republic of Congo produces 64% of the world's cobalt. Palladium is produced dominantly in Russia, hafnium in France, but you will see that the standout is that the vast majority of critical mineral resources are produced by China. And the light rare earths and the heavy rare earths, 95% of those were produced by China. And this is what people is considered to be a risk. Of course, if there are geopolitical issues between China and other countries, then there can very easily be a very rapid cutoff in the global supply of these really critical elements. One example of this recently was in germanium, where the US decided not to export their technology for microchips to China because their technology for these nanochips they felt could be used in development of weapon systems. In response to that, China said, okay, well, we're not going to allow sale of germanium on our open market. And this is what led to the, you may remember a few years ago, there was a shortage of microchips. So if you ordered a computer or something like that, there was a period where we had to wait up to 6 months in order for things to be produced because there was no production of these microchips. I mean, that's just an example of how a sort of geopolitical debate can lead to a kind of a shortage of production of these things. Microchips, well, okay, we need these for lots of things, but if this if this started to, if a similar thing rose up that involved rare earth elements, then we would have real problems producing wind farms, which are predicted, which are planned to be one of the major renewable energy sources. So this is a real problem. And this has led to the EU developing their Critical Raw Materials Act, which is basically an act that's recently been passed through the EU, European Commission, in order to safeguard the supply of critical mineral resources within the EU. Within the EU, you can see here, this is where we sit in terms of lots of these critical mineral resources. We import 100% of a large majority of them. Even iron ore, you would think sitting in Sweden that we would not require, that we would not need to import iron ore, but we do. The EU in general has to import iron ore. Our consumption increase is greater than our production of these mineral resources. So we are dependent on these open markets. We are dependent on countries like China to continue selling their resources if we're going to continue to manufacture our car batteries and various other things. Can recycling provide our metal requirements? So what this shows is a sort of summary of the proportion of recycling that occurs for these different chemical elements. All of the dark purple and blue colors indicate fairly good recycling. The transition metals and base metals and precious metals, things like iron, copper, zinc, lead, gold, and so on, they're all recycled fairly well. But all of the critical elements that I've talked about, lithium, tellurium, and of course the rare earths, they are recycled to a less than 1% of those are recycled. And this is partly because of the way the modern technology is. These elements are mixed into glasses and things like that, which makes it very difficult and energy intensive to recycle them. And in many cases, we just don't have, we haven't yet developed technology to do it. The technology is lagging behind. All of the elements that are really well recycled, this is technology that's been developed over the last half century. So these are things that has been in place over the previous periods of time, and we're not there when it comes to critical mineral resources. So what do we do about it? We need these critical mineral resources to allow us to transition away from fossil fuels. Obviously, then we're going to have to open more mines, right? Everybody should agree with that. It's obvious from the data I've just presented that the best solution is to, or that at least one solution is that we're going to have to produce more mineral resources. However, as I'm sure you're all sitting there aware, not everybody wants to open more mines. Not everybody has a positive sort of vision of the mining industry in their heads. This is a very large mine, the Yanacocha gold deposit in Peru. It has a very big footprint. Besides these 5 large holes in the ground, there are also 5 very large leaching heaps where the ore is leached of the metal. Not everybody wants to have that on their doorstep. And there's a lot of recent examples within Sweden of where mines have been proposed at various levels of sort of exploration, and they've all come up against very strong opposition. Here, Scandi Vanadium have looked into extracting vanadium from the alum shale. Of course, this is one of the problems with talking and thinking about opening new mines, is that the mining industry has a very long history, and rock types such as the alum shale have a very long history in terms of environmental related issues with mining. The alum shale was used at various points during the last century to try to produce uranium, fossil fuels. It was used as a direct energy source and so on. And we know that there are large areas with large waste piles from this, the use of this material. These types of environmental problems, they stick in the mind. They don't disappear very easily over time. So whenever anybody suggests something to do with black shale related mining, and particularly the alum shale, it leads to conflict and opposition. Other examples are, so this is just something from Naturskyddsförening. They are an excellent organization, and they have a very interesting attitude when it comes to mining, because of course they see the necessity for mineral resources to combat or to move away from fossil fuel energy, but they also see the potential local environmental impact of mines, and they're kind of stuck somewhere in between, where they oppose mines on the local scale, but they also are keen on the idea that we transition away from fossil fuels. So it's a difficult position to be in. Another example that I'm sure you may well all be aware of is Norra Kärr, which is a rare earth element mineral deposit on the which is very close to Vättern, and it, as a mineral deposit, it would be Europe's biggest REE producer by far. It would be an extremely useful, valuable REE commodity, but it is sitting in a sensitive area which is close to Vättern, and has, obviously there's concern that there would be contamination of waterways and groundwater and things like that. So this is where we kind of currently sit. We need to produce more mineral resources. Western countries in general tend to be pretty much against mining. But if we're not going to mine, where are we going to get the resources from? Is it really okay to just export this social and environmental debt to developing countries? This is what we've been doing for many years when it comes to, for example, as you see here in these different, the press release from SVT, that when we buy new iPhones and various different things that require batteries, of course we require cobalt, and the vast majority of that comes from the Congo. And there is different types of cobalt resource one can purchase from the Congo. Some can be guaranteed from coming from a certain mine that's run by a certain company, but there's also Congo that is produced on the open market, which is sold by local dealers, and that's basically artisanal mining, which is driven by everybody and anybody, including groups that involve child labor. So there is a big environmental and social debt or risk with just continuing to import mineral resources that are produced in other countries. Another example would be REE. So this is a picture of the Bayan Obo REE deposit in Inner Mongolia, which accounted for almost 50% of global REE production in 2019. There have been reported to be severe environmental problems in the surrounding areas related to mining of this deposit. And of course, if we continue just to allow REEs to be imported from China, then we don't have any control then on the environmental regulation surrounding mining of the resource. If these mines were located in Western countries, particularly Sweden, we would have much stricter control on the environmental regulation. So the question then, is it really morally okay to allow us just to continue to import and use resources from other countries when we have viable resources available in our country? So this is my last slide. Just to summarize, essentially what I've shown is that renewable energy sources are very mineral intensive, particularly for the critical materials. The EU currently imports the vast majority of critical raw materials. They have set up the Critical Raw Materials Act, which is supposed to facilitate the development of resources within the EU and to ensure to diversify the sources from which we import materials so that we're not so reliant on one or other country to import raw materials. So that's a kind of a positive step forward. As I see it, the big problem is that many in society don't see a link between consumption, our own personal consumption, with where the resources come from, which is the mining industry. When it comes to farming and things like that, we're all fully aware where the produce that we consume comes from. However, when it comes to mineral resources, that link is not seen. We do not see the mining industry as we view the farming industry. We don't see them as producing necessary commodities that we need for our way of life, to build houses, have cars, infrastructure. And that's even without the requirement to move towards renewable energy. And I think this is a problem. And particularly in cities where people really consume modern technology, and many people tend to be against mines because they see the environmental legacy. But and of course there are environmental problems with mining, but we don't necessarily see the positive or important sides of what mineral deposits and the mineral resources industry produces. So we're left with these questions. I think they're sort of moral questions, essentially. Should we open more mines in Western countries like Sweden? I would say, yes, we should. We should try to be self-sufficient if we could. Wherever we have a mineral resource, of course, we need to evaluate whether the actual mineral resource, what the cost, the balance between the local environmental cost is and what we gain from it in terms of resources. But there's every industry that we have, there is a cost. It's the same for anything, and there needs to be a cost effect kind of balance analysis done. And I don't necessarily think that is done. I think a lot of opposition to mining is emotional and is carried out in a less than systematic way. Can we continue to export social environmental problems to developing countries? Well, from a moral perspective, I don't think we should, but from a geopolitical perspective, I think we're at great risk if we do continue to do that. I think we need to look at making sure we can produce the resources we're going to need to allow us to transition away from fossil fuels. And particularly as even when we get away from a climate related issue, as fossil fuels run out, which they inevitably are going to do, we're going to need to have fuel and energy sources which are driven by alternatives. So I think inevitably we're going to have to end up producing more mineral resources within our own countries. Okay, that's my final slide. So I would like to say thanks very much. Or just to say here are the references. So if anybody wants any of these, then they can just email me and I'll send these reports and so on. Okay, I stopped sharing.
All right. Thank you very much for that very interesting presentation.